take a look at number 33 from our textbook to try to work out a multi-force static equilibrium problem. So we have a bag that has a weight, according to the problem, of 325 newtons. It's connected to a rope that has tension T3, and that is connected to two other ropes with tensions T1 and T2, and the angles that they make with the ceiling or roof or whatever you want to call it listed above. So there's a bunch of numbers there, but what we need to do in order to solve this problem is recognize that there are technically 2 points of contact going on. And if we're going to solve any sort of problem using free body diagrams and net force or dynamics equations, we need to take a look at those 2 points of contact separately. So if we separate it into 2 kind of systems, we've got the bag of cement connected to the rope, and then we've got the 3 ropes interacting with each other. We can't solve this problem unless everything is separated. We can't solve it all at once, essentially. If we do, we have to make some assumptions that it's best not to make. So first off, let's establish that in this lower system, that the bag of cement held up by the rope, if we were to write a free body diagram for it, we would have the weight force Fg going down and the tension force T3 going up. Now, I prefer to write it as force of tension 3, but since the book is using capital T's for tension, that's what we'll use. And since the system is in equilibrium, it's not accelerating, a net force equation for that in the vertical direction would be tension 3 minus Fg is equal to 0, which means that tension 3 must be equal to 325 newtons. Now that's key. Without knowing that, we can't solve the rest of the problem. It's going to be kind of academic. Now for the upper little system there, if we were to write a free body diagram for that, we would have tension 3 pointing down, tension 2 pointing off at an angle, and tension 1 pointing off at an angle. And in this case, if we want to solve the problem, we have to break everything up into components that align with our traditional XY axis. So T3 is already lined up with our axes. T1 and T2 need to be separated. So the angle theta 2 would also be down below that line if we think of it in terms of if the parallel line with the roof is this dotted line here, then we have parallel lines cut by transversal, opposite interior angles are congruent, etc., etc. We can also say that this is theta 1. So we can split T1 and T2 into components that are along the x-axis and along the y-axis. I'm going to do that down below here just to formalize it. Remembering that if we're going to turn a force, a velocity, anything into components, we have to make that the hypotenuse of a right triangle. Once we make that the hypotenuse of a right triangle, we can make the legs of that triangle into component vectors. So this would be T1x, and this would be T1y. We can say that T1x would be equal to whatever tension T1 is times the cosine of theta 1. And when we put that into a net force equation, we have to make note that it is going to the left. So it's going to be a negative component. T1y will be equal to T1 times the sine of theta 1. Now we are given what theta 1 is in this problem, so that'll help us be able to solve for what T1 is. And likewise, if we do the same for T2, make it the hypotenuse of a right triangle, then draw on the legs of the triangle, we can write out what the components are. I forgot to put theta 2. Oh no. With that all set up, now we can go ahead and take what we've established from our free body diagram, that there are these three forces interacting, but two of them are at angles to our coordinate system, so we split them into components. Now we can take anything that's going in the x direction and anything going in the y direction and write net forces for it. So in the x direction, if I write a net force equation for that, that point of contact right here, go ahead and label it, let's call it A. So for point A there, and I guess we can call this point B. Go into more detail than's necessary there. For point A, we can say that in the positive x direction, we have T2 cosine theta 1 minus T1 cosine, oops, oh my goodness, get my 1s and 2s mixed up there. Theta 2 and T1 cosine theta 1 should be equal to 0 because it is in equilibrium. Recalling that we can say that that's equal to 0 because it should be the net force is equal to m times a, but since the acceleration in the x direction is 0, the net force must be equal to 0. From that, we'll be able to do a little bit of comparative work. We're going to be ultimately solving for multiple variables using multiple formulas, or sorry, simultaneously solving multiple equations. So two unknowns, two equations, we can solve it. For the y direction, we'll have T2 sine theta 2 plus T1 sine theta 1 minus, and here I'll just put it as T3 to keep it as non-numerical as possible, would also equal 0 because, again, in the y direction there's no acceleration. Now we have two equations with two unknowns. We've got T2 and T2, T1 and T1, and we also have T3, but T3 we know is equal to 325 newtons. So at this point it becomes an exercise in algebra. And my personal opinion in how to solve this problem is not to try to do a linear combination, because that would just be ugly. You'd have to multiply both equations by like top one by a sine theta and the bottom one by a cosine theta. It'd just be really ugly. So the best method here in order to get to a solution is solve, oh my goodness. To get to a solution is take the sigma fx, solve for T2 maybe. So it's going to be some expression for T2, and then sub into the sigma fy. Then you should have just T1 in the sigma fy equation, and you can solve for it there. So I'm going to go ahead and get that set up and then return with a solution. So as you can clearly see, here we get the solution. I took the sigma fx equation and solved it for T2 just by adding the T1 factor over and then divided by the cosine theta 2. I took that and then substituted into the sigma fy equation where the T2 factor was. I noted that sine theta 2 times something over cosine theta 2 would be tangent theta 2. So I did that at the next step when I also factored out T1 from the first two terms of the equation. I added T3 to the other side. I then divided that big ugly trig thing under T3 to get an expression for T1, plugged in all the bits and bobs, made sure I was in degrees mode, and I got 253 newtons. And then I went back to my equation that I had set up for T2, plugged in T1, the angles, and I got 164. So I believe the back of the book said it's supposed to be 165, but I think they didn't round something the same. I don't know. Either way, this is the solution I got, and we're good. That's the answer.